Alright, so here I am presenting some joint work with Alex Paysalkovich, a social scientist at Facebook, and Dave Rand, a professor at Yale. So the fundamental question we're looking at here is, why do humans cooperate? And this is well studied in domains where cooperation yields long-run self-benefit. So this is where there's a repetition, for example, in economic games. You can kind of grow to know that the other person is going to cooperate and you benefit in the long run. Or, when your reputation is on the line, it makes sense to cooperate. However, it's known that people cooperate when it's not in their economic self-interest to do so. And we see this all the time, from one-shot prisoner's dilemmas to when you're walking down the street and you give a homeless person $1. That is not in your economic self-interest to do so, yet people do it all the time. So behavioral economists use social preference models to understand this altruistic behavior in economic games. And behavioral economists also have a sliding scale of model complexity. So on the lowest end, we have a general framework, which is basically just a restatement of the game parameters. This kind of assumes that everyone is basically the same, the representative agent model, and it's just the game parameters which determine if you're going to cooperate. And this is kind of the least complex version of the model. And the most complex on the other side of the spectrum is a fully heterogeneous framework, which assumes everyone has unique preferences as kind of this special snowflake. So the natural question here is cooperation a heterogeneous trait? Is everyone kind of unique in their ability to cooperate, or is everyone kind of the same and it really just depends on the situation? So, and a quick aside on kind of models and model evaluation. So George Box famously said, all models are wrong, but some are useful. So the question here is, what is usefulness in these models, and how would you even measure that? So the key insight here is that we use out-of-sample prediction to measure usefulness. Basically what this means is, we have a training set, we build a model from that, and then we do out-of-sample prediction on a test set. And a model is good and useful insofar as it can predict data that is not seen before. So what did we do? We took about 1,000 Mechanical Turk workers, asked each of them about 20 decisions for a total of 21,340 total decisions. Each decision was in the form as follows. Each person decided between a selfish option where they received X cents and the other person received Y cents. These are just randomized. And a cooperative option where the participant would receive X minus C cents, so they're incurring a personal cost of C cents, and the recipient receives Y plus C times F, where F is this public good multiplier, a number greater than 1. So as you can see, as F gets larger, the participant pays a small cost to give the other person a very large benefit. So kind of we're studying the interplay here as those parameters scale, when do people start to cooperate? And then from that data, we built some models. First, we add pairwise interaction in square terms for all the features to kind of expand the feature space we're looking in. Then we divide the data into a training set, which is the first 15 decisions each person made, and a test set, which is the last 5 decisions each person made. Then we train a 5-fold cross-validated regression model on the training set, which is the features is our input values, which we'll talk about in a little bit. And out of that, we're trying to predict, did, in this decision, this person cooperate? 0, no, 1, yes. And how did we do? So the first model we tried is this kind of least complex one, the representative agent model. Basically just using game parameters to predict if people cooperated. When we do that, we get an AUC of a little less than 0.7, so not too bad. On the other side of the spectrum, we have the fully heterogeneous model, the best kind of model you can imagine, because this allows everyone to have their own model coefficients. And when you do that, you get an AUC of about 0.9. So these kind of represent two extremes for our models. And then between these, first we have a two-type model. And what this basically does is we classify people into 2 different groups, cooperators and non-cooperators, depending on how much they cooperated in the training set. And so as you can see, you get a large bump over the representative agent model by introducing this 2-type framework. And when you do that, this indicates that capturing individual cooperation history leads to much higher predictive power. You get a huge bump up. Then when we go to 3 types, we also get another increase over that. This suggests that, and you can see here that the 3-type model is basically as good as the fully heterogeneous model. And then of course with 4-type model, we're kind of halfway between here. So as you can see from how this kind of flattens out, there's something kind of powerful about three types, because once you have three types, that basically explains almost as much as the fully heterogeneous model. So there's something special about three. So what are these three groups? First, we have the most cooperative people. These are the people who cooperated in 6 or more of their 15 training decisions. Next, we have the intermediately cooperative people. They cooperated in at least 1, but fewer than 6 of their 15 training observations. And finally, we have these defectors, the least cooperative. And these people cooperated in none of the 15 observations. They were complete defectors. So the next question is, what is the nature of these groups? So what we did is we collected demographics that people commonly thought were associated with cooperation. Across psychology, economics, and philosophy, there's these kind of core principles of people that these people think are kind of related to cooperation. You can think of belief in God, religiosity, utilitarianism, all these kind of ideas. So we collected about a battery of 80 different demographics, and then we built a model trying to predict which cooperative type you were in, the most cooperative, intermediately cooperative, or the least cooperative, based on these demographics. And when we do that, we get an AUC of about 0.54. And knowing that the base rate for AUC of a null model is 0.5, this is not very good. So this suggests that you can't actually predict what cooperative group people are going to be in if you know all this kind of demographic about them. This suggests that cooperativeness is orthogonal to other demographics and is a natural kind. And this is kind of building on this idea of a cooperative phenotype that's been put forth by our lab. We also did a robustness check. The machine learning is a top-down approach, but we also have a kind of bottom-up approach, thinking about it from a different way. So, in the fully heterogeneous model, each participant was assigned their own model parameters because we're interacting it with subject-level fixed effects. So, you can kind of think about this, kind of slicing in a different way, that each participant is kind of a point in an n-dimensional space, where n is the number of kind of parameters in your model. So the natural question is then, can we cluster these participants into groups in this space? So what we do is we run k-means, and here's what we get. Very similar to the machine learning approach, you see that once you introduce even 2 clusters, you get a huge bump in explaining the variance. Moving up to 3 allows you to explain even more of the variance, but then once you get to 4, it kind of asymptotes again. So the fact that this functional form reflects the insights from the machine learning approach kind of reflects its validity. So overall, I think this work has 2 kind of prongs and kind of deep conclusions. Those on kind of the nature of prosociality in economic games, and then on methodology and social sciences in general. So for prosociality, previously people have used ad hoc social preference models, these 2-type models, 4-type models, or sometimes a custom utility function to kind of look at this. However, here we have a tunable way to evaluate an array of quantitative theories in a kind of scalable way. And also, to victory for sparsity. 3-type models does almost as well as a heterogeneous model, which you can think about since we had 1,000 participants, it's an 1,000-type model. So this shows that you only need a couple of groups to explain all the variance in these different people. So, this is kind of substantiating the cooperative phenotype. Methodology side, it's using machine learning in the social sciences in a way that hasn't really been done before. We use prediction as a proxy for feature importance to compare lots of different qualitative theories in a very quantitative way. And this gives insight into mechanism in a kind of unstructured way, which previously wasn't possible. Thanks.